and multiple imputation. I'm kind of obsessed with these things because they like follow me wherever I go. It's a very, very large topic, and I kind of struggled in terms of what to present today. So my talk today is going to be slightly different to my previous presentations in the sense that I'm not going to show you guys a single equation, okay? There's not going to be a single beta anyway, right? But what I am going to do instead is talk to you about missing data, talk to you about why you should consider it, why it's important. I'll talk to you in a very high level conceptual way of how to do a multiple imputation, some things you should watch out for. And right at the very end, I'll show you an example of code of how to implement it. And the reason I'm showing you some code is not to freak you out, but just to demonstrate the fact that once you understand how to do an imputation and how to do it well, the implementation of it is like 5 or 6 lines, okay? Right, so missing data. Why should you care about missing data? Well, first of all, like I said, missing data is everywhere. It's in every single data set that I've ever examined. And if you have a data set that doesn't have missing data, please send it to me because it'll make my life so much easier, okay? Then also, you know, practically, when you'll submit your papers to like the BMJ and the New England Journal of Medicine, which you'll all do, they ask you to do these things called equator guidelines, like the strobe checklist and the PRISM checklist, I think it is. And one of the questions on there is, did your data set have missing data? And if it did, how did you deal with it? So these journals are forcing you to deal with missing data. And that's a good thing, right? It is a good thing. But what if you ignored your missing data? What would happen to your results? So in the best case scenario, if you ignored missing data, you would lose precision and power in your analysis. So what that means is your confidence intervals would be much wider than they would otherwise be, which is like a little bit annoying, but maybe it's not the worst thing that could happen. But the worst thing that could happen is that you seriously bias your results, yeah? And if you have biased results, then they're not generalizable or meaningful or, you know, interpretable really. So missing data is a problem, but whether your results are going to be lacking power and precision or being biased, it'll depend on the type of missing data you have. Because your missing data isn't just missing, there are different types of missing data. And depending on the type of missing data you have, you're either going to be losing power or you're going to be introducing bias. Okay. So then let's talk about the types of missing data that we have. So there are 3 different types of missing data that can happen. And I'm going to tell you the 3 different types, and I'll give you a couple examples of them. Okay. So the first type of missing data that happens in our data sets, and this is my favorite type of missing data, this is when data is missing completely at random. So what that means is that there's no systematic difference between missing and observed values. An example of that would be, you know, like you have your Excel sheet of data, and every once in a while when you're not looking, your daughter comes and deletes a cell, okay? She's not deleting them systematically, she's just randomly coming in and playing on the computer. Yeah, so that kind of missing data, there's no systematic difference between whether the data is missing or observed. Okay. Then you have a type of missing data, which is kind of okay, and we can address it. It's called missing at random. So in that case, there are systematic differences between missing and observed values, but these differences can be explained by other data in the data set that's been observed. So for example, say in your data set, you have questions about social class and salary, okay? And you notice that salary information is missing. But then when you try to look at it and you try to understand why the salary data is missing, you will notice that people of a higher social class tend to not report their salary because they don't want you to know that they're earning the big bucks, okay? So you have missing data in salary, and there are systematic differences between observed and missing values in salary. but that missingness is explained by your social class, okay? Then you have data that's missing not at random. Now, this is the worst kind of missing data to have, and it's really annoying, okay? Because this type of missing data is there are going to be systematic differences between observed and missing values, and these systematic differences are going to remain even after you take all other observed variables into account, okay? And that's a little bit difficult to get your head around, but basically what I'm saying is that there's going to be a relationship between the propensity for a value to be missing and the value itself. So for example, people with severe depression don't take part in a survey about depression because they're depressed, okay? And that's the worst kind of missing data to have. Now, I don't know if you'll remember in my previous talks, I talked about the fact that there's no statistical test for confounding, and likewise, there's no statistical test for the type of missing data you have. You kind of just have to use your substantive knowledge on how the data has been collected and the context to make, you know, reasonable judgments about how your data is missing, okay? And just to say that in real life, you're probably going to have a mixture of these three different types of missing data. Your data set is probably not just going to be completely missing at random or completely missing at random. It might be a mix of the two. But for a moment, let's just assume we have these three different distinct types of missing data in our data sets. And we ask, well, what would happen if we did a complete case analysis in each case? Yeah. So what would happen if, say, we have a data set of 100 people, for example, and about 50 of them have missing data. What would happen if we remove those 50 people and we just did our analysis on the remaining 50 people? If our data was missing completely at random, yeah, meaning that there's no systematic difference between the 50 people that we're examining and the 50 people that we've dropped, right, yeah, what would happen is we just lose precision in our results. Our results are not going to be biased because the 50 people that we're examining are identical to the 50 people that we've dropped. The only thing is we've lost power because instead of examining 100 people, we're now looking at 50, okay? If our data was missing at random, the 50 people that we're going to be examining will be systematically different to the 50 people that we've dropped. Yeah, because in the example I talked about earlier, we're essentially going to be dropping more people from a higher social class. And so we're going to end up with biased results. And likewise, if our data was missing not at random and we dropped the people who had missing data, we'll get biased results. Yeah. Now, we can address some of these problems, okay, using something called multiple imputation. So if we did a multiple imputation when our data is missing completely at random, that's good because we can increase the power of our analysis. So we'll essentially be bumping up our analysis from 50 people back to the 100 people. If our data is missing at random and we do multiple imputation correctly, we can reduce the bias in our results. Yeah. And if our data is not missing at random, it becomes much more complicated. And basically, you have to do a bunch of sensitivity analyses, and multiple imputation may not necessarily solve all your problems. Okay. So before I continue, do you have any questions? Some of this will become clearer as I go along, but if you have any questions of anything I've said, just ask me quickly.
Can I ask quickly, Snehal?
Of course.
Sensitivity analyses. So is there a right way and a wrong way of doing it? Because it's something you see mentioned a lot, but not always reported in papers. So should it be, like you said, where you look at your analysis just with your sort of included patients, and then you compare that to the entire data set, or is it, yeah?
So that's a great question. Some of the examples I'll show you later might help with that, but very quickly, in my opinion, I think that your imputed analysis, where you've dealt with missing data, should be your main analysis. And then in sensitivity analysis, you can discuss, you know, tweaks like, oh, if I remove these people, this was what would happen and that sort of thing. But in my opinion, your mean analysis should be done on your imputed data set, because that would mean that you have less bias and more precision in your results.
Right, thanks.
But we're going to come back to what you should present in the paper and how later on as well. So cool. I can't remember what I'm going to tell you next. Oh yes, right. So just to end the slide, imputation can solve some of your problems if your data is missing completely at random or missing at random. So, well, that's great, but I haven't told you what an imputation is, right? So this graph over here, this little picture over here, which I've stolen off Google, basically describes what a multiple imputation is. So imagine we want to examine the relationship between blood pressure and cardiovascular diseases, okay? And in our data set, 20% of people are missing information on blood pressure, okay? So that's the white in this box here. So what we do is we predict the missing blood pressure for the people who have missing blood pressure using other data in the data set. We're basically using a series of regressions to predict blood pressure using all other information available in the data set. Okay, and that's the dark blue in these boxes here. But because we're predicting someone's blood pressure and we don't know if what we've predicted is what their actual blood pressure is, we need to account for that uncertainty in our analysis, yeah? And so the way we do that is, instead of predicting blood pressure for people once, we predict it many times. We predict it about 20 times. And so we create 20 different complete data sets, okay? Then we analyze each complete data set on its own and get 20 sets of results. Essentially, you're doing the same analysis 20 times, okay? And you get 20 sets of results. And then what you do, you obviously don't want to present 20 sets of results because that's just crazy. Also, more seriously, each result doesn't account for the fact that you have uncertainty in the predicted blood pressure. So what you do is you take all those 20 results and you pool them together into one result that you are going to present. And that pooled result, which is based on those 20 sets of analysis, has wider confidence intervals, allowing for the fact that there was uncertainty in blood pressure for 20% of your population, okay? So essentially, a multiple imputation is a two-step method, where first you create different plausible imputed data sets and you do your analysis, and then you combine your results from different data sets together. Okay, and to say that it's really accessible, you know, it's available to do in Stata and SPSS, SPSS, R, and I don't know, a whole bunch of other stats packages that I've probably never heard of. But I just want to emphasize that while it's really easy to implement, you need to carefully think about its application, okay? Which is what we're going to talk about now. Oh, yeah. Before we do that, actually, I just wanted to emphasize as well that imputation is justified under the assumption that your data is missing completely at random. I mean, it's also justified under the assumption that your data is missing completely at random, but missing completely at random is the most stringent kind of assumption that you could make, whereas missing at random is a less stringent assumption, and we can do stuff to try to ensure that your data is missing at random. And I'll come back to that in the next slide as well. So when you're going to do a multiple imputation, what variables should be included in your imputation models? Yeah, what variables should you be using to predict your missing blood pressure? So obviously you want to include the variable that has missing data in it, like blood pressure on the previous example. But what else do you want to include in your imputation models? Well, you want to include all substantive model variables, even if they don't have missing data. So in the example of examining high blood pressure to cardiovascular diseases, I imagine you'd be using sex as another explanatory variable. And sex probably has no missing data, but you'd include it in your imputation models because sex will probably help you better predict whether the person has high blood pressure or not. Okay. Other things you want to include in your imputation models are anything that would strengthen your missing at random assumption, because this will reduce your bias. Okay. And my top tip, yeah, is a great predictor of missingness, whether it's included in your substantive models or not, usually is something like social class. Yeah, social class is a great predictor of missingness because people, in this case, people of low social class are more likely to have high blood pressure. So whether or not you're looking at social class in your main models that you want to present in your paper, it doesn't matter. You want to include social class as a predictor of missingness in your imputation models. Okay. The other thing to consider is how are your variables in your imputation models distributed? You're going to have to tell that to your stats program. And your variables are either binary, categorical, or continuous. So a binary variable is straightforward. It's, for example, yes, no, male, female, that sort of thing. Categorical variables can be further subdivided into ordinal or nominal. So for example, social class and education would be ordinal categorical variables where there's an order to it. Yeah, nominal categorical variables would be things like, I don't know, region of residence, or like NHS trust or something like that, yeah? And then continuous variables are obviously just variables that can go from, you know, 0 to infinity or negative infinity to infinity. But when you have a continuous variable, you need to consider how the continuous variable is distributed, okay? And in the case of blood pressure tends to be normally distributed, so you don't have to think about a transformation. But if instead of looking at blood pressure, we were looking at triglycerides is not normally distributed. And what the imputation does with continuous variables is that it assumes that it is normally distributed. So you want to strengthen the assumption of normality for your variables. And so because triglycerides isn't normally distributed, you'd log transform it, make it more normal, do your imputation on the log transformed triglycerides, and then transform it back to the original scale after you've done your imputation. And I'll show you an example of that, I think, on the in a couple slides. So it sounds like a lot, and I won't lie to you, dealing with missing data does take a lot of time. And, you know, sometimes I get a little bit frustrated that like you spend weeks dealing with missing data and it ends up like being 2 lines in your paper, but they're 2 important lines, okay? And after you've dealt with missing data, there's some key salient things that you should present in your publication. So when you start writing up your publication, you want to talk about how you got to the sample for your analysis. You want to talk about the range of missing data in your data set, because I think it's very different imputing data that has missingness, you know, up to 20% in variables versus imputing 80% of your data of a variable. You want to talk about how the sample with complete and missing data were the same or different. And obviously then you want to talk about how missing data was handled, okay? And this sounds like quite a lot to put into your paper, and your paper only has like 3,000 words, yeah? And so you don't want to spend all those 3,000 words talking about missing data. And so the way to get around that is to use figures. Figures are the best things in the world, guys. So this is an example of some work that I've recently done where we used a figure to explain how we went from 19,000 people in the biggest sample for analysis, and we ended up with 9,000 people, okay? And then in the text, when we talked about missing data, we used this kind of language. So we talked about missing data ranged from blah to blah. So we're talking about the range of the missing data. And then we say what we've imputed, what had missing data that we were using multiple imputation to fill in. So we talked about missing information for covariates, early life and adult SEP were imputed. Basically our covariates, early life SEP was our exposure of interest, and adult SEP in this case was our mediator. Okay. Then we're telling the reader what our imputation models included. So imputation models included all substantive variables for our main models, plus our main predictors of missingness, which improves the missing at random assumption. And in this case, our main predictors of missingness were age 7, internalizing and externalizing behavior and cognition. Then we tell the reader how many imputed data sets we had, and in this case, there were 20. And we say that imputed results were similar to those obtained using observed values. And in this case, we've only presented the former because they were generally similar. Yeah. So although a lot of work goes into dealing with missing data, it can be quite succinct in your actual publication. And I just want to show you a little bit of code of how to deal with missing data, just to emphasize that once you understand how to deal with it, it's like, what is this, 10 lines of code? And so as an example here, I've just brought in my data set. And when I brought in my data set, I realized that BMI at 45 and BMI at 16 were not normally distributed. But the inverse of BMI at 45 and inverse of BMI at 16 were normally distributed. So I transformed my data. And now I'm going to use inverse BMI at 45 and 16 in my imputation. And so I no longer need BMI at 45 and 16. So I drop those variables, yeah? Then in this bit of code here, all I'm doing is I'm saying, well, these variables are binary. These variables are continuous. These variables like social class, they're ordinal. This is a nominal variable. And these variables here, like sex, age, whether you're on cholesterol and antihypertensive drugs and so forth, they have no missing data and they're auxiliary. They have no missing data, but they're either in my substantive model or they're good predictors of missingness. Yeah, so that's all I'm doing here. I'm just defining the distribution of the variables that are going into my imputation model. And then this is just how you tell Stata to do an imputation. And what I wanted to highlight in this is here, this add 20 basically saying to do 20 imputed data sets. And here, this our seed business is just to say that when you do a missing multiple imputation, there's a random element in it. And the first couple of times you do a multiple imputation, you're probably going to end up doing it several times. And to ensure that you end in the same place all the time, it's good practice when there's a random element to set a seed so that you always start the random element in the same place so you can replicate your results. That's just a good practice point. If ever there's something random in your analysis, you want to set a seed. Some useful resources on missing data, because I've literally just scratched the surface and it's a really complicated topic, yeah? But some really useful sources are this BMJ article over here, which is written for clinicians, and it's all about like what you should watch out for when you're doing a missing data analysis. I highly recommend it. And this website here is for practical tips on how to handle missing data in Stata. I'm sure there's equivalent stuff available in for R and SPSS. And just to say, if you do go onto that website and try to understand missing data, don't expect to go through the modules in a day. It'll take you a couple of days because it's really involved, but it's a really good website. And to end, I just want to say, even if you didn't understand anything from my talk, that's totally fine. But this is just to tell you what not to do instead of dealing with multiple imputation. Please don't replace any missing values with the mean of the observed values. Don't make a new category for a level missing if you have a categorical variable. And if you have repeat measures on the same individual, don't replace a missing value with the last observed value, because doing any of these things can seriously bias your results, okay? So like, even if you don't listen to anything else I said, just screenshot the slide. And that's all that I have to say on missing data. I could go on about it for hours, like I said, but I just wanted to give you a quick idea of the things that you should watch out for, and to emphasize that while it's complex to understand, once you understand it, the implementation is easy. And so I'm happy to take any questions if you have now.